Now with probability distribution tables, we can easily get common measures that we get for any sort of distributions. So these measures are expected value, variance, and standard deviation. So that's one big advantage of putting it into tables. We can easily gather this data. Now the first one, expected value, is represented by this Greek letter mu, or E of x. It's a measure of the average or the mean of our distribution. In context, it'll represent the expected number of whatever x represents. So we'll go into an example after this, but the example talks about the number of TVs sold by a salesman per day. So essentially x, or E of x, would represent the average number of TVs sold on any given day, or the expected number to be sold based on the probability's likelihood. Now the formula for determining E of x is the sum of x multiplied by its corresponding probability. So this weird looking symbol here represents a sum. So essentially, once we have our table with x and a probability of x is equal to x, and we had different entries here, what we'll do is we'll multiply these two numbers together, add that with the multiplication of these two, add that with the multiplication of these two, so on and so forth. Now you can see why the table is so useful, because we can get that data straight away. Now the variance is something else we can get. It's represented by VAR of x. It's a measure of the spread. So essentially, what the spread is in general, and in particular this context, is it's how likely other outcomes are to happen away from the expected value. So let's say the expected value lies at this entry in the distribution. It doesn't have to be exactly at one of the numbers in the distribution, but let's say for argument's sake that it is. Then the variance is a measure for how likely other outcomes are to happen away from this. So for example, if these were 0.33 probability each, then the spread would be relatively high because the other outcomes are just as likely to happen as the expected outcome in the middle. However, if we had a distribution like this, 0.9, 0.05, 0.05, then the spread would be very low because the mean is still the same. The mean is still at the middle, and we have a symmetrical distribution like we have above. However, it's very unlikely that we're going to get those alternative outcomes. It's very likely that we're going to stay close to the mean, which is at that middle term, 0.9. Now, that's essentially what variance is. It has no inherent meaning as such, but it's more for comparison. If you want to compare other distributions, let's say if one has a higher variance, one has a lower variance, then you could say this one has a higher spread, the other one has a lower spread. It's more for comparison rather than measuring something that happens in real life. Now, the formula for variance is E of x squared minus the mean squared. So first we have to calculate the mean, and we also have to calculate this E of x squared. It's a very similar calculation to this one up here, except you just square the x term. So when you multiply the x and the probabilities together, you just square the x term or the outcome term before you multiply it with the probability. But apart from that, it's the same calculation. Now, the last measure that we talk about is standard deviation. It's not mentioned too much in the textbook, and that's just because it's very similar to variance. However, standard deviation is important to talk about because it's a very common measure in practice in general, and it's also talked about with the other types of probabilities that we talk about in methods. So it makes sense to talk about it here as well, and how it relates to variance. Now, if you do further, you should know about standard deviation, what it measures. It's essentially just another measure of the spread. It's represented by this symbol sigma, or SD of x. And the formula is just the square root of the variance. So you can see once you get the variance, it's very easy to calculate it. Now let's go to an example where we calculate each of these things. And this example talks about a number of televisions sold by a salesman per day. And it's shown in the table below. The number of televisions is represented by the variable x. So this row here with the numbers, that has the number of TVs sold, and then the number below it represents the corresponding probability of selling that many TVs. Now it's worth saying that these probabilities add up to 1, And this should always be the case for any sort of probability distribution. So if you want peace of mind, then just add up the probabilities and you'll get a total probability of 1. Now, to calculate the expected value, we just use the formula as mentioned above. Now, we don't have to rewrite the formula. You could just write down the calculation. So for example, it'll be 0 times 0.03 plus 1 times 0.05. Again, just multiplying the corresponding outcome with the probability. Plus 2, 0.03, and you can see this is pretty tedious. And then once you compute this in the calculator, you get a certain number. In this case, it will be 3.05 TVs. Good to use the unit when you can as well. In this case, it's a number of TVs, so I just write 3.05 TVs. Now, in terms of interpreting this result, it just means that the average number of TVs sold is 3.05 statistically. So obviously you can't sell 3.05 TVs because you can't have a decimal number of TVs. However, it's important to note that this is purely a theoretical number, the same way that the probability of flipping a head when flipping a coin is 1/2. We know that we won't get exactly half the flips to be head, but in the long run, when we do infinitely many trials or infinitely many days in this case, then the average number of TVs should be getting closer and closer to 3.05. So it's more of a statistical thing rather than a practical thing. Now, to calculate the variance, we just used the formula before, and we know that for the formula, we needed E of x, so we've already got that from above. We also need E of x squared though. And you can see it's exactly the same process, except you just square the number of TVs terms. So 0 squared times 0.03 plus 1 squared times 0.05 plus 2 squared times 0.03. Oh, that should be 0.3, sorry. That term in the table. And then we just continue that for the rest of the values in our table. So I just put the dot, dot, dot. And we end up getting 10.95 for this. Now, once we have that, we can determine the variance as E of x squared minus our mean, all squared. I'll put that in square brackets just to make it clearer. So it'll be 10.95 minus 3.05 squared is equal to 1.65. Now, for variance, it's not very common that you see it with the unit. You can put it if you'd like, and technically it is in terms of TVs. However, I'll just neglect it for now because it's harder to interpret it as a physical measure. Like, it doesn't really mean much when you say, oh, the spread is 1.65 in terms of the number of TVs. So there's no point including it. Just say it's 1.65. Now, the next part of the question is a bit more unique. It's kind of an extension of the first probability distribution. We'll just have a read. The bonus is given out if the salesman hits a certain number of sales. If the salesman sells 5 TVs, he receives $100. If he sells 3 or 4 TVs, he receives $50. If he doesn't reach either of these targets, he receives no bonus. Let B represent the bonus amount in dollars. Describe the probability distribution for B. So what this question is asking of us is to create another distribution table, except this time it's measuring something different. It's measuring the amount of bonus in dollars. So the table would look like this. So the first term would actually be lowercase b to represent the specific outcome, but then the actual event is receiving a bonus. So the first row would have lowercase b, the second row would have capital B equals lowercase b. Again, the lowercase b represents our specific outcome. So in this case, we can either receive no dollars, $50 or $100. So that will be the entries in our table. Now, to determine the probabilities of receiving these bonuses, we'll just have to look at our question and see how that corresponds to our original table, because you can see this heavily relates to the original distribution for X that we had before. So he only receives $100 if he sells 5 TVs. So we have to look at the probability of selling 5 TVs, and that was 0.17. Now, if he gets $50, that means he sold 3 or 4 TVs. So let's get the probability of selling 3 or 4 TVs. Them added together is 0.45. Now, if he gets no bonus, that means that he sold neither 3, 4, or 5 TVs, so it has to be part of this set here. So if you add all these probabilities together, you would get 0.38. And if you added all these probabilities individually together, then we would expect that these add up to a probability of 1. Now, if we want to determine E of B, this in context would represent the expected bonus that the salesman receives. We would just have to do the same calculation as before. So E of B is equal to this multiplied by this. I mean, you're multiplying by 0, so there's no point in even including that in the calculation. You can if you want, but when you type it in the calculator, it just means it equals 0. So I wouldn't say there's much point. So you end up getting 50 times 0.45 plus 100 times 0.17. And if you evaluated this on the calculator, you will get $39.50. So this is the expected bonus that he receives. Again, he's not going to receive this bonus exactly, but if you had infinitely many days, even if you averaged out all the bonuses that he received, he would get $39.50.